one of the shortest videos that I've ever done, so I probably should have tacked it on at the end of the other one, but I feel like that one was getting too long as it is. So we're just gonna go with it. But yeah, this is gonna be dealing with the relationship between equilibrium and free energy, because as I've said before, everything in chemistry is essentially like related to each other. You can build upon one concept using another. And something that I forgot to mention in my previous video, which I'm gonna do right now, is what's called standard free energy, which is essentially the same thing as what we did before. It's just that now everything's at standard state, as in its ideal state, which is 1 atm and 1 molar of concentration. That should be a 1. That looks really ugly. I'm sorry. 1 molar and 1 atm. And to write down your standard Gibbs free energy, it's the same thing as before, where it's your delta G, except now you have a little naught symbol. So it's delta G naught is equal to delta H naught minus T delta S naught. And it's still dealing with it the same way that we dealt with everything else, as in you find your delta H, you find your delta S, you just put them together. It's just that now this is what would happen ideally at standard state. And when it doesn't have the knots, it's what's actually happening, essentially. So yeah, that's the major difference between them. So don't freak out if you see something with like these little knots and you're like, oh my God, what does that mean? It's the same process. You still just find your sums, or like your change. Yeah. You find your changes in enthalpy and entropy and your temperature. You plug them into the formula and you just solve. Make sure your units are the same though. But yeah, it's the same thing when you're working with it mathematically. It's just this is ideal. That little line shouldn't be there. But okay, now actually dealing with equilibrium and free energy. So what we're going to do is talk about this. And essentially, you have a relationship between free energy, standard free energy, and Q, which is your reaction quotient. And that relationship is delta G is equal to delta G naught plus RT ln of Q. And Q is your Q from equilibrium. Like products or reactants at not equilibrium, you're good. It's nothing crazy. And then your R is your R constant of 8.314 joules per mole K? Yeah, joules per mole K. So then essentially when this is at equilibrium, so we're finally actually dealing with equilibrium like I said we would be. So at equilibrium, your delta G is equal to 0 and Q is equal to K. So under these conditions, we can rework this formula that I just gave you with their relationship to say that 0 is equal to delta G naught plus RT ln of K, because now we're at equilibrium, delta G should be 0 and Q is equal to K, so you can just plug those in so that we can rework our formula to say delta G naught is equal to RT ln negative RT ln of K. Let me do this differently because it looks kind of funky. But yeah, so at equilibrium, your formula transforms to delta G naught is equal to negative RT ln of K. And so, yeah, with this formula, if you have a high K value, then your reaction is going to be more spontaneous. Therefore, your delta G naught is going to be negative. So yeah, and then because we're dealing with equilibrium, and with equilibrium when we have our formulas, it's like, oh Jesus. Okay, whatever. It's like A to B, and it has these double arrows. So what this now means is that if your delta G naught is negative, then it's going to be spontaneous in the forward direction. So delta G naught negative, spontaneous is in forward direction. And now, if your delta G naught is positive, that means that it'll be spontaneous in the reverse reaction. So what that means is that, let's say that your A was a solid, no, your A is a liquid and your B is a solid, your reaction would be spontaneous in the reverse, as in you would go from products to reactants more likely than you would go from reactants to product, just because your liquid is more favorable than your solid. So yeah, that's what it means by spontaneous in the reverse reaction. It just means that going backwards, it would be more likely to happen than if it were to be going forward. Right. So then the final concept that we're going to be going over is just kind of your relationships between K and delta G naught. So relationships of K and delta G naught. So essentially what the relationships are is if K is greater than 1, product favored, then your delta G naught is going to be negative and therefore spontaneous. And if K is less than 1, it's reactant favored. Then delta G is going to be positive, delta G naught. I forgot the naught. It's going to be positive, which will be it's non-spontaneous in the forward direction. And if K is equal to 1, which means that both products and reactants are favored. It just means that they're equally favored, by the way. Then your delta G naught is going to be equal to 0. Under standard state conditions, which is what the naught means, that it's at standard state. And yeah, that's pretty much it for equilibrium relationships with delta G. So yeah, that's it for this module. Like I said, this video was really short.